Hello, welcome to MSE210. The course is titled Engineering Measurements and Data Analysis. So this is going to be week one. So this week we're going to be focusing on the learning objectives. Are going to be introduction to the course. We'll talk about essentially the process of engineering measurements, and then we'll talk about the data representation. So these are the topics we're going to be discussing. So these are the list of topics over here. So there's going to be introduction to the course. We'll do like introduction to the main topic, talk a little bit about methodology, precision and accuracy, measurement, traceability, and calibration, the scientific principle, and then where engineering method and statistics are going to be used, or in a case, we'll have few definitions talk in regards to probability, and then we'll have few more definitions, and then we'll talk about different data types, sampling, and then potential sources of error, which will be critical evaluation, and then we'll talk about data organization, frequency table, and then finally for this segment of the video, we'll conclude by talking about experimental design and ethics. So this is going to be the very brief thing about this. And then if you're watching this video, so this is going to be more of like a lesson or a classroom kind of an experience. And then if you can print and then you can follow along on your notes as well. So without further ado, so the course itself is going to be just kind of like reiterating what we said. It's going to be an introduction to methods to collect and analyze engineering data. We'll have topics including engineering data representation, talk about discrete and continuous probability density function, engineering measurement, error analysis. We'll talk some extent about sensors, noise, and then segment noise processing, and then we'll do something known as an hypothesis testing, which is basically going to be a hypothesis basically means an theory or a working theory that you might have, and then we'll talk about how to statistically evaluate whether or not your theory is valid or not. And then we'll talk a little bit about regression, and then we'll go to design of experiment. So this would be the brief overview of all of the topics we're going to be covering in this video series over. So the introduction, essentially the accurate data measurement has been very important from a significantly long time back. A lot of these standards were introduced to basically ensure when you're having like machines, so the performance is met, and then you have items and you're trying to put them together. So you're going to make measurements of one item and then the other items. So you want to make sure, particularly if you're going to be manufacturing these at different places, particularly with the advent of mass manufacturing, it becomes important that you measure all of these properly, and then all of the physical attributes and all of that actually makes sense. Similarly, measurements are going to be very important to control theory. So now robotics is kind of coming back again, and so then you have the question or the problem of placing the robot. It's known as a SLAM problem. So essentially simultaneous localization and processing. So essentially you want to basically make sure you know where the robot is. So you might have noise that's coming in your sensor. You might have somebody kind of like disturb maybe some robot around. So all of that are going to cause a lot of issues. So then we're going to be measuring, and then we have to kind of like differentiate and then use this in the control problem. And then also if you're kind of trying to optimize the power that's coming out of say the wind turbine, or like if you have a fuel cell, you might want to control or to do some diagnostics. In all of those cases, measurements become very important. So oftentimes we're going to make kind of like a success and failure and judgments based on the measurements. So what do we mean by that is a lot of times you might actually have we define these terms later on, but we'll have something known as an intervention, where you might have a specific action and then you might need to make some measurement. A very simple relevant example in here is, for instance, if you have an outbreak and then you're trying to do some different interventions. So you say, okay, so restrict the number of people moving around, or we want to waste medicine. So all of these are going to be different interventions, and the hope is the intervention that you're doing is going to be beneficial and then actually maybe reduce the outbreak. So that is the main objective. But we cannot just like hope for things. So we want to make sure we have some concrete backing, or we basically collect data. And then what is going to happen is anytime you have a data, there's going to be some uncertainty in the data. So all of that need to be taken into account. So in a more general case, you might have kind of like measurements, for instance, for satellite navigation. You might need to have ultra stable clocks. So your GPS system is actually based on a very accurate clock. And then so the nuts that you order from supplier, so if you order from, say, if you order from McMaster, so sponsored by them, and then you buy the bolt from somebody else, and then you want to make sure that if you have the specified number, that they're actually fitted together. And similarly, in food production, you have to maintain temperature. Very simply, if you're making biscuits, it's important. But more importantly, you would have, so if you want to kind of say, make sure that food doesn't get spoiled, you need to kind of like measure the temperature over time, and then make sure it doesn't go outside of some specific acceptable range. So all of that kind of gets important, and so we want to deal with this. And so the measurement and statistics are going to be important in a lot of fields, but then our main focus in this course is going to be things that are going to be relevant from the engineering perspective. So if you just do kind of like a worldly of the things that engineers actually measure, so this kind of gives you some representation here. So we measure things like speed, length, mass, and then we have like generator energy. So you can, it's kind of one analysis. This is kind of like measurement of dimensions and so on. So we actually, as engineers, do a lot of measurements, and then all of these need to be done. In some sense, we have to do it properly. So in order to do that, there are established standards. So the International Standard Organization, or ISO, this is basically the sort of different standards. So ISO is one of them, and then we have different standards in different regions. We have the Bureau of Weights and Measures. So we have the ASME, which is American Society of Mechanical Engineers. They define some structural standards as well, maybe like dimensions of sections and so on. And then in this is basically be done in Canada, so we use borrow a lot of our stuff from ASME, although we do have a CSME, which is the Canadian Society of Mechanical Engineers. They have maybe a few variations of the standard, but we follow a lot of the international standard. Similarly for electronics, so you have the IEEE standard. So this is kind of has actually like a range of things that come under the umbrella of IEEE. So you have essentially like communication standards, have the Wi-Fi, and all of that basically have to follow one particular IEEE standard. And then you have, say, the USB, and all of that would kind of come under a different standard. So generally what happens is each country might actually have its own institute, which kind of looks around and kind of like maintains a standard within that particular country. On a related note, or on the side, so we might have building standards, each established for a different country. So British Columbia, so we have a slightly different code from, say, Ontario. So if you're building in provinces in the same country, there might be different standards. So the overall objective would be so kind of have slightly different standards, because there are going to be slightly different varying threats and other unknowns that are going to be affecting the system. So there's going to be slightly different standards, but overall the main objective is to maintain safety. And then kind of like basically, if you have some failure, all of these standards and all of the societies, they kind of analyze this failure and then try to see if they can figure out what the problem was or what the cause of the failure is. And then ideally, you want to make sure that we don't repeat that. So that's one of the main reasons all of these standards comes in for buildings. But with respect to the other standards, so those are more established to say that if I'm basically doing one measurement in one country, for instance, if I design a weight to be 1 kilogram here, and then if I take it to India, or if I take it to the United States, it's still 1 kilogram. So all of that standards are established so that you have the same results coming in different countries. And also, if you want to do trade, it is going to be much, much easier. So now we come to some general terminology. So with respect to measurements, so metrology is the science of measurements, and a metrologist is the person who is actually going to be performing all of these experiments. So the function of the metrologist is to define internationally accepted units for measurements, promote units for measurements in practice, establish traceability. So we kind of see what these are in just a bit, and kind of like documenting the values, establishing. There are three main types of metrology. First one is scientific metrology. So this is defines and organizes the measurement standard and undertakes research into new or improved measuring techniques. For instance, you might come up with a new instrument, or right now they just have recent redefined the kilogram. So there is kind of before that is actually fully adopted. There is some scientific process that goes there. We have industrial metrology, which ensures adequate functioning of measurement instruments in industry, such as those used in manufacturing, process, and quality control. We also have legal metrology, which verifies and ensures the application of the measurement standards that enable economic transactions. So, for instance, if you want to buy and sell between people and between industry, this would be that's where you. So as engineers, we continuously take measurements, and then we need to ask ourselves how accurate, or is it accurate enough? And then if the device that we're using make the measurements is being set up correctly, and then also how crucial this measurement is. So what we mean by that is, if I'm basically measuring my shirt, it's important. Maybe if I put on weight, not fit into the shirt, but it's not super crucial if I'm off by maybe a few millimeters or few centimeters. I can still use the shirt. But at the same time, if you're maybe designing an engine cylinder inside an engine, if you're off by 1 or 2 millimeters, so if you're too big, you're going to seize inside the engine. If you're too small, the gap between cylinder piston ring so large that you're not actually going to generate any power in the engine, basically be venting exhaust gas. So your application is also going to play a crucial role in deciding whether or not your measurements are crucial, or how crucial your measurements are, and what's an acceptable range for these values. So just very, very briefly, we have to be aware that even very, very simple or seemingly simple mistakes can cause a lot of issues. So there are few examples here. Great Kurtzen blunder. So there where the probe to Venus, it basically used a different conversion. So there was an error. Instead of 25.4 to convert from millimeters to inches, they had used 25.4. So this seems very simple, but then it kind of is a very large error. And so this basically the Kurtzen programmer made a crucial error, and then it was basically led to like a $2 million loss. And then you have the Tokyo Disneyland Space Mountain derailment. So this was kind of again an incorrect conversion from imperial to SI units. And then I'm not sure if you might have already heard about the NASA Mars Climate Orbiter, actually a while back, not the recent one. But before that, again, there was an issue with converting the thrust between imperial and metric units, and which basically caused it, instead of the orbiter to orbit Mars, it basically went and slammed in. Not great. And then here back in Canada, there is a famous like a flight incident known as a Gimme glider. So again, what happened was in Air Canada, so they had just been converting from metric to imperial, from imperial to metric units, and then there was some miscommunication. So they were thinking they were loading 22,300 kilograms of fuel. Rather, they ended up loading 22,300 pounds of fuel. So 1 kilogram is 2.2 pounds. So they basically maybe like what they loaded about 45% of the fuel, and so halfway through they ran out of fuel. Fortunately, it was kind of a more funny story where the technically an aircraft which ended up gliding and then landing in the Canadian Armed Forces base in Manitoba, Imlay. So that's where the name comes from. So sometimes these are just become like funny anecdotes where kind of like a professor can just make fun of it, but then as an if you're actually in the field, it's not so nice. And then if it ends in tragedy, it's even. We need to be careful about all of these stuff, and then also you want to make sure that there are other mistakes that might creep in which you want to avoid as well. So Really quickly, so the section summary, so if you've gone through section, so you should be able to answer why measurements are important, and then what metrology is, and then what a metrologist does, and then you should be able to answer the three different types of measurements that are done as well. So next, we'll start looking at some important concepts with respect to measurements. So the first property we're going to be looking at is known as precision. So precision basically defines how close your measurements or outcomes are related to one another. So essentially, if you have measurements all over the place, it's less precise. And then if you can kind of like get them to closer and closer together, data basically becomes more and more precise. So the example here in this case, if you look at this corner over here, so this is basically a fairly precise measurement where all of the data are clustered together. So the second concept is accuracy. So it defines how close the measurements are to the true value. So in this case, if you're kind of like playing darts, your true value or your target is going to be the middle point over here. This would be fairly accurate and where everything is kind of lumped together. So in reality, what happens is you don't often know the true answer. For instance, if you're actually making your measurements, so then you don't actually know the true answer, so you don't actually know how precise or accurate your result is. In that case, we have to do some kind of like some further analysis. So what we basically do is the best we can do is we can basically think about how wrong, quote unquote, our answer might be, which leads us to the concept of uncertainty. So what that means is we want to basically see that if you have an answer, we can do some analysis based on all of the data that we collect, and then see how or get an idea of how wrong our answer might be. So the next concept that you can look at is known as repeatability and reproducibility. So repeatability is basically like looking at the closeness or agreement between repeated measurements of the same thing. For instance, I could be measuring a voltage, so I'm going to be taking the first voltage, and then I'm going to be taking the second voltage of the same value, assuming it doesn't really change, and then it needs typically carried on in the same place. So for instance, I'm going to be doing my office, there's nothing else that changed with the same equipment, and then it's carried out in the same manner, kind of like measuring twice, thrice, and so on and so forth. Reproducibility is what happens is when somebody else is doing a similar experiment but using maybe like a different set of equipment under different circumstances. So this would be, say for instance, if I'm doing some research and then I come up and say, hey, this if you basically use control methodology, you can improve the energy performance of the wind turbine by 20%, and then I kind of like publish the result, and then it goes into the scientific literature, and then somebody else is like, hey, I don't really trust this professor. So what they would do is they will set up a similar experiment and then see if they're able to reproduce the result. So essentially they would kind of use their own equipment, still kind of like they need to maintain, obviously if they do a completely different experiment, it doesn't really make sense, but they'll basically be carrying out a similar experiment but under different circumstances by a different person, and so that becomes the reproducibility. So essentially they're going to be reproducing my experiments. Then it basically adds credibility. So an example would be, so if you basically think about when they were thinking about gravity, so you have been reproducing those results again and again. Similarly, Einstein's relativity, so they have like different groups of scientists been observing effect of the way it was initially established was when they observed a very far away star during an eclipse. They could basically see that light actually bent around the sun. So you can kind of repeat the same thing maybe at a different eclipse or under different circumstances, and then you establish that indeed the theory is true. So that will be reproducibility. So then the next concept is concept of tolerance. So the tolerance is the maximum acceptable difference between the true value of a quantity and the value that it's specified, and the value it's specified. So essentially, if you think about measurement, so if I basically set a tolerance on the length of a bar, then I say I want it to be exactly 100 millimeters, and then what happens is I say, okay, you know what? maybe you can't get it to 100 millimeters, so you apply say a plus minus say 1 millimeter or plus minus 10 millimeter tolerance. That basically means I'm accepting anything from if it's plus minus 10, anything from 90 to 110 millimeters, which is kind of what your tolerance is going to be, or tolerance of accepted range. The next thing we're going to be looking at is units of measurements. So there are basically two main types of units. The first one is known on the left here are known as base quantities. So base quantities, so these are actually established by SI convention. Base units are going to be the length, which measures how long or short a substance is, mass, which is how heavy. Actually, weight is actually a force. Mass is what's the mass of a substance. Kind of is related to weight, but mass is slightly different. The third is time. So actually you have a watch. So that's another standard unit. So you basically measure how long something has passed. The next fourth unit is electrical current. So if you connect volt to a battery, then current flows through a circuit, and so that's another fundamental unit. Measure the current. The next one is temperature, so it's how hot or how cold substance is. The next one, the one after that, is the amount of substance, mole or moles of a substance. So basically, kind of measures how much quantity of a substance is, or basically kind of a measure of the number of atoms. And the next one is luminous intensity. So it's kind of like how bright a light is. So right now I'm recording this, so I have basically a lot of light here. So if I use the light meter, it'll actually tell me how bright the environment is, and then you can actually measure it. So these are the units. So the luminous intensity is measured, length is measured in meters, mass in kilograms, time in seconds, current in amperes. So here are the symbols that we use. And then temperature is in Kelvin. So oftentimes you might report it in Celsius. So, but there is an easy conversion between Celsius and Kelvin. Unfortunately, we do sometimes report the temperature in Fahrenheit, and you can convert it. And then on honesty, the Fahrenheit scale and the Celsius scale are technically documentation defined in terms of the actual SI unit Kelvin. So it's like all kind of like tied back. And then obviously the moles is a scientific experiment. You can measure the amount of atoms in number of moles, and then you can. So on the right column over here, we have derived units. So these are actually one or combinations of one or more of these base units. So an example would be if you look at area or volume. So area is kind of like the surface area. So area is squared meters, basically like a length times another length. Volume is a third length. So if you have speed or velocity, it's the rate of change of position, meters per second. Symbol is m over s. Acceleration is rate of change of velocity or speed. Actually, it's rate of change of velocity. So this is going to be in meters per second or meters per second squared. You have mass density, kg per cubic meter. Current density, which is amperes flowing through a specific area. And then you have molar concentration. So if you kind of have a small volume, you can calculate how many moles are there, and then based on that, you can calculate kind of it's kind of related to mass density, but here it's going to be the molar density. And then you can think of luminescence, which is candela per square meter. So it's like how bright, so luminous intensity is going to be the total light coming out, and then the luminescence is what is the light per unit. So why are these units important? So you should always add or subtract units with or quantities with the same units. So you cannot basically add a meter to a kilogram, remove a meter from a kilogram either. So you make sure that they're the same quantities. Then you can multiply and divide different quantities, get from one base unit to another derived unit or between derived units. And then when we are comparing base units, so this is called dimensional analysis. So if you think about the force times the velocity, you look at the units is times meter per second, and then bring it down all to the base units over here, this basically becomes kilogram meter squared second to the -3. So this is actually the power consumed by a fan or propeller. For instance, if you have a boat, the boat actually develops a thrust, so it's going to apply a force, and then it's going to be pushing water from the backside at a specific velocity. So if you multiply the two together, you will get the power that the motor or fan actually puts out. Same concept applies to fan as well. Or if you think about a wind turbine, you can think about the force that the air mass applies on the wind turbine times the velocity is going to be some amount of power that's exerted onto the wind turbine, and so that you can convert that into how much electrical power is withdrawn. So in that case, if you multiply the voltage times the current, so if you look at that, the voltage is actually defined as kilogram meter squared second to the -3 ampere inverse, and then you multiply an ampere, you'll actually notice that you get the same unit as before. So this again is electrical power. So what that means, you can now compare these two units. So for instance, if you have an electrical outboard motor on your small boat, what you can say is you can calculate based on the efficiency or what have you. You can say how much power is being put out by the motor, and then I can think about how big of a power supply I would need. And then once I have the power supply, I can multiply it by time, and then I can look at the capacity of my battery. And so then what this means is like you can basically compare, even though they are like seemingly different, they might actually be talking about the same underlying concept. So this is very useful in doing that analysis. So these are a few very simple expansions. So these are the different symbols and extensions. So a lot of times what happens is you might need to have like very large, very small measurements of something. In that case, you can apply the SI subscript here. So you can read through this. So it's not like something you can go ahead and read through this. But the most common ones is basically the unit of 1 here. So you can get larger here. So you have 10, you have deca, and then multiply by 10, you have hecta, kilo, and then mega, giga, tera, and so on and so forth. And then you can get things smaller. 1/10 is deci, 1/100th is centi, 1,000th is milli. You can keep going down here and going down here. So you can have up to pico and femto are really common. So for instance, if you think about it, so 1 kilowatt of power is actually 1,000 watts. 1 micron or 1 micrometer is 10 to the -6 meters. So if I apply 5 volts across a 100 ohm or 1 kilo ohm resistance, then the current consumed is going to be 5 times 10 to the -3 ampere, or it's going to be 1 milliamp. And another example would be if you think about small batteries, you often see their capacity listed in milliampere hour. So this is kind of like a combination as well. Milliampere is 1,000th of an ampere, and hour is actually 36,000 seconds. 3,600 seconds. So you can actually kind of do the calculation there and list the values there. And a final concept you can look at is going to be the concept of traceability and calibration in the instrumentation. So calibration basically talks about comparison of an instrument or an artifact against a more accurate standard. So for instance, if I have a ruler here, I can actually calibrate it with a more standard ruler, or maybe take a vernier, which is going to be a more standard ruler, and then I might be able to calibrate how accurate. Error, this I would probably throw it out. But if it's a more accurate instrument, there is probably like a tuning mechanism that's available that you can basically reset the zero or kind of change the gain or what have you. Then accreditation is the comparison laboratory in a specific field. So they independently assess audit, show that they are competent. So the laboratory is competent in doing that. International standards are agreed upon procedures on how a laboratory should carry out accurate measurements on a specific item. So the ISO based in Geneva kind of tasked with ensuring and then establishing these standards. And then this kind of gives you the measurability tracing. So typically what happens is you define the units, there is a realization or a primary standard. For instance, if you have a meter, it's defined in terms of like a physical phenomenon, so you can define that. And then you have a secondary standard, which is calibrated against this primary standard. And then you have a master working standard, which gets calibrated against the secondary reference. Then you have a measuring equipment, which every so often gets calibrated through the working standard. And then you have the end user over here. So this would be the typical hierarchy here. So typically you have a parallel standard. So a lot of it is actually held in the SI standard, but if it's going to be an actual physical, now everything is actually being physical phenomenon, so that makes it easier for everybody to actually establish. And then you have a working values, the primary standard, secondary, and tertiary standard. And then what happens is you can basically, if you have an equipment, you can potentially send it to the manufacturer who would get potentially calibrated. So previously there was actually a prototype kilogram standard, and that was basically what was used to establish all of the other standards around the world. So there's actually an interesting thing that actually happened, which actually caused everybody to from the standard kilogram to a different definition. They actually found out that different kilograms all around the world were actually not agreeing with each other. So essentially, they were platinum blocks which were defined to be 1 kilogram. Then there were like 6 identical kilograms that were made, and then they were kept in different places. And then every so often they would bring it back, measure, and then compare. And then because that's the definition of the kilogram, you can't basically say whether or not like 1 kilogram increased or decreased. Just know that it's changed. And so then that caused a lot of problem. And then now they've actually changed the actual physical definition. And there is actually a very, very interesting video. I'll try to link. So very quickly, so what we covered in the section or segment was kind of looking at the difference between precision and accuracy. We looked at, so you should be able to answer what is the difference between repeatability and reproducibility, and then what they actually refer to. And then we talked about base units and derived units, and then you should be able to answer how traceability and calibration basically work. So the next topic is is the concept of the scientific principle, where we basically are going to do more rigorous analysis of kind of going about trying to figure out a solution to the problem, or establishing whether or not a solution is correct or better than the existing problem. So the main question is, why do we bother about scientific principle? The first thing is to avoid bias. So what that means is you might actually you might be very invested in your theory, and then you don't want that bias to play into your findings. So if you follow the scientific principle, then you're less likely to be influenced by bias. We want to get as close to the truth as possible. So then again, the scientific principle allows you to do that. And then as engineers, we try to solve problems in the interest of society by making it efficient. So we basically would try to apply a more efficient use of scientific principle. And then the engineering or scientific method is the approach to formulate and solving kind of like very challenging and useful problems within society. One interesting thought is basically all of the scientific principles are established, and we have the scientific theory. There is a in sociology of scientific knowledge, Planck's principle is basically states that scientific change does not occur because individual scientists change their mind, but rather successive generations of scientists have different views. So more colloquially or funnily, this or informally, this is referred to as science progresses one funeral at a time. Essentially, it's kind of like a funny way to think about it, but nonetheless, all of the accumulated knowledge at the end is being verified by, and kind of like as the new scientists come along, might have a new idea, but nonetheless, they have to challenge the existing order and then use the scientific principle, data collection, rigorous analysis, show why their theory or their methodology is actually better than the existing one. So the main scientific principle is, firstly, we develop a clear description of the problem, then we identify the problems, the important factors that affect it, at least we have a tentative idea. Then we propose or refine a solution. In this case, we have to state the limitations or assumptions. Then we would collect data, so conducting experiments. Then we manipulate our model. So if your data doesn't fit, it have an initial or preliminary assumption of how things work, then you would have to change your model accordingly. This helps or develop a new solution. And then we confirm our solution, conduct more appropriate experiments, and then ultimately draw a conclusion or recommendation. And so, even though the scientific principle has been well established, we should, as scientists, be aware of some of the blind spots that the principle might have, and basically do our best in data collection or experimental design to make sure we don't get overly biased the results or get biased by a assumption. So then the next thing is we're going to talk about the engineering method and statistical thinking. So physical laws are used to design or improve processes, and then same thing when you're doing experiments, get data from scientific principle. So for instance, in the engineering concept, engineers at drug companies or medical devices may be interested in studying the effectiveness of an invention. In an ideal world, every experiment basically produces the exact, perfectly repeatable uh, and uh, realizable result. You experiment again and again, you get the same answer. But reality is, however, messy. Oftentimes, there is inherent variability. Not be able to clamp. So, for machining a part, not be able to clamp it with the same amount of force. Or if you clamp it with too much force, it might bow. Clamp it with too much force, there might be vibration first run. Maybe somebody turns on an AC when it's too hot, and then there's heat dissipation that might change. Or the other way is the AC turning on actually affects the voltage just ever so slightly. Uh, and then similarly, the next door they might be turning on a motor or an oven. It changes the RPM ever so slightly, and the frequency might also change, and so that could affect what your performance is. And then the equipment might be sensed to some vibrations, and then what happens is it's often too expensive to measure every single thing that can actually affect your reading outcome. Sometimes it might be practical, not even thought of. And so then the question is, given or to put simply, is given unavoidable variations between products and people and the need to perform limited experiments, you have to think about how realizable our findings are or how valid our findings are going to be. So this is where the statistical thinking comes about, where we're saying, like, instead of thinking about one experiment, we're going to see like if we can do a lot of experiments, and then can we look at the variability in the data and still make a valid conclusion. So that's where statistical thinking is going to be applicable concept of engineering. So now that we have looked at the need for statistics, so we look at some definitions within statistics. Firstly, the science of statistics deals with the collection, analysis, interpretation, and presentation of data. So organizing and summarizing the data, generally, this is called as descriptive statistics. So then what happens is there are two ways to summarize data. They either do it graphically, which would be like plots and graphs that you might create, or you may do it numerically, where you might find the average, variance, and so on. The second type of statistics is drawing conclusions from quote unquote data. This is known as inferential statistics. So here need background on probability and probability distribution. So we might small set of experiments and then try to infer some thing about a bigger population, or what are the likely outcome your experiments might come about or your intervention might have on a full population. So we'd also use probability to determine how confident our conclusions will be. So this is where we're going to be looking at. So basically, First one is called descriptive statistics, and then differential statistics that are kind of related but are looking at the problem from different. So the next set of definitions we're going to be looking at is probability. So probability is the mathematical tool used to study randomness. So it deals with chance or the likelihood of an event occurring. So what happens is statistics and probability are kind of like different faces of the same coin. Statistics is dealing with a lot of experiments or a big population. Probability is kind of like trying to pick one or two people or one or two experiments from the sample, and then we are looking at what the likelihood of producing one particular result. So an example would be, so you might say that there is an 80% chance or 80% probability of it going to be raining today. Vancouver, it's probably much higher than that. But nonetheless, what you can actually do is you can look at how much it's rained over the last, say, 100 years, and then plot all of those values on a daily basis, and then that will give you like a statistics of the rain event. So then if you look at the relation between probability and statistics, if you have a very, very large collection, probability of an event occurring becomes the number of occurrence of the said event within the population group or the data set that you're looking at. So again, coming back to probability and statistics and engineering concept, so essentially measurements and process always include variability. Statistics gives us the framework for describing this variability and for learning about potential sources of this variability. For instance, if you basically took a steel and then or mild steel, and somebody told you strength or fatigue strength of the steel is 125 megapascal. So fatigue strength is strength of repeated loading. Then there's going to be some variability. Right? So there might be some changes that occur due to the surface finish or temperature, and then how the process, how the steel had been manufactured, and a lot of the other things. Then the question is, what does it actually mean when somebody says endurance limit is 125 or endurance strength is 125 megapascal? So it basically means, at least in the concept of endurance limit, it is a stress at which 50% of the samples do not fail. That means if you take a bar and then stress it to 125 megapascal, it's bending, actually circular bending, so then 50% of the samples would not fail. So then what we can think about, how do you improve this? So instead of this being 50%, if I wanted it higher, so what I can do is I can actually lower the stress level. So instead of 125, depending on how the material actually behaves, I might actually be able to come up with a lower stress, which will give me say a 90% reliability or 90% survivalship. This is where we use statistic and probability engineering concepts. So moving on, we will look at few more concepts or definitions of statistics. So first one is, in the statistics, we generally we want to study a collection of persons or things. So this is known as a population. So this is the collection of people or things that we're actually studying. Conduct the study in a population, we basically select a sample. Essentially, if you think about having a big jar of candy, so we pick one, so that's just basically sampling the population of candy. And then the sample is basically subset. So if I have, say, a box of M&Ms, and I pull out one M&M at a time, so then I'm sampling, and then what I could potentially do is draw 10 M&Ms and then make some conclusion on the different colors that are basically available then. Another example would be if you have an election or a census poll, basically can't actually survey the entire population, it's expensive. Then what happens is you can basically get a subset of the population, census form gets sent, and then we assume there basically is going to be some margin of error, and then this gets reported in the lecture, or when this basically gets written. So statistics is basically a number that represents a property of the sample. For instance, you have a sample, so then might say like 50% of the sample actually had a television or a 50-inch television or larger in their home. So then that becomes a statistic number. And then a sample must contain the characteristics of the population in order for the sample to be known as a representative sample. So what that means is if you want to say survey the population of Canada, then you don't want to basically just pick everybody, say from the province of Quebec, province of British Columbia. You want to basically pick enough number of people that they are repeated or kind of like distributed all over. Similarly, if you are basically looking at a box of M&Ms, you don't want to basically pick maybe like a box which is somebody ate all the yellow M&Ms and you don't want to sample it. You want to basically pick a sample that's going to be representative of the overall population. So in the field of statistics, so generally we have variables. So this would be kind of denoted by capital letters X and Y. So this is a characteristic of interest for each person or a thing within the population. So very quickly, so a variable may be numerical or categorical. Have numerical variable weight, pounds, or time it takes to do some task in hours. And then you might have categories. So you might have categories such as political affiliation, eye color, gender, ethnicity, and so on and so forth. So then we basically have these that basically collect. So this is a variable. That means like if you pick one person, so weight, they might be weighing say 50 kilos. There might be another person that weighs 70 kilos. So the weight itself has only a value, or it takes on a value when you pick a sample, but the weight itself can vary. So that's why it's a variable. And since so we would denote the weight as X, and then you might basically have height of the person in say millimeters or meters, and then that will be another variable. So again, if you just say height, this doesn't have an inherent value associated with it, but you can say what is the height of a particular person, then your variable actually takes a value. Similarly, you could have the temperature, which does kind of like vary, but then the temperature at the current instant might have a particular value. And then data are the actual values of the variables, and they may be numbers or words, and then datum is the singular form. So let's look at a very simple example. So if you have, so we can determine the key terms in the following study. We want to know the average or mean amount of money of a first year college student spend at ABC College on school supplies that does not include books. We randomly surveyed 100 first year students at the college. 3 of those students spend 3 of the students spend 150, 200, and 225 respectively. So then we can look at the different terminology in terms of what's the population, what's the sample that's specified, the parameters, and so on. And so this would be a good time for you to pause the video and then see if you can answer or figure out these questions. So coming back, so if you want to answer these questions, so the population that we are looking at is the population is going to be all the freshmen or first year students at the college, ABC College in this term. So let's then, what is the sample that we're looking at? Here sample, so in this case it's not actually specified. So this could be anything. So this could be the sample of 100 students that are basically taken. So the parameter that you're looking at, what is the variable X? In this case, it's going to be the amount of money spent excluding books by the first year students. And the particular statistic we are looking at, mean, and then the data that we have going to be some samples. X1 is 150, X2 is 200, X3 is 225, so on and so forth. So let's look at another example. So determine the key terms referring to the following study. An insurance company would like to determine the population of medical doctors who have been involved in one or more malpractice laws. The company selects 500 doctors at random from a professional directory and determines the number in the sample who are involved in the malpractice. So again, so we're going to be looking at the different statistics that we just defined, kind of like the population, what is the random variable, and then what is the metric we are basically studying. So again, you can pause the video and then try to answer these questions. So in this case, the population is going to be all medical doctors listed in the professional directories, and the parameter that we're going to be studying, proportion of medical doctors who are involved in one or more malpractice. The sample is going to be 500 doctors that were randomly selected from the professional directory. The statistics is that we are interested, again, the population, that kind of goes back to the parameter. And the next one, the variable, is number of medical doctors who are involved in the malpractice. And then the data is going to be either yes or no. So yes being that they are involved, B or not. So if you finish the segment, so what you should be able to answer is what is the scientific principle. You should be able to explain the concept of probability and statistics from an engineering concept, and then you should be able to define two different categories of statistics, and then you should be able to define different terminologies, population, sampling, data, etc. And then if I give you given a problem, you should be able to identify all of these different parameters in the study. So next, we're going to look at the types of data that we'll be dealing with. So the first one are qualitative data. So these are results or categories of describing things. So an example would be hair color, blood types, ethnic group, or the car that a person drives. We typically would represent this as a count or a percentage. So you might basically say a percentage of people that have a black hair color or a blood type of A1 positive, and so on and so forth. So the next type of data that we'll deal with are quantitative data. So these are numbers. So this would be kind of results from counting or measuring attributes for a population. An example would be the amount of money people have, pulse rate, weight, number of people in your town, number of students who undertake the statistics course, and so on and so forth. So qualitative data could either be discrete, where they are like separated into chunks, or continuous. So discrete data are results of counting. So it could be kind of the number of calls that comes in, number of televisions a person owns, and so on. A continuous variable or a continuous statistic, which is something that we continuously, be something like the heights and so on. So continuous would kind of like something that varies continuously from 0 minus infinity plus infinity. So an example here would be, so you can work collaboratively and then determine whether these are quantitative or qualitative. So an example would be, you look at the number of pairs of shoes, and then if you're quantitative, you can decide whether they are continuous or discrete type. So generally, if you have something which is number of, then it's going to be countable, and then it's going to be discrete. So an example here, the number of pairs of shoes, types of car you drive, and so on. So now again, you can pause the video and then see if you can answer this question. So in this list, basically A, B, and G are quantitative discrete. So number here, A, and then D is number of classes you take per year, and then G is number of correct answers in a quiz. These are quantitative and continuous. B and E are qualitative, like the types of car you drive, and then the type of calculator you use are qualitative, and then so the rest, like the distance, is continuous, and then the weights are also continuous, and then they are quantitative random variable. So the next concept we're going to be discussing here is the concept of sampling. So gathering information from the entire population is going to be fairly expensive and sometimes almost impossible. For instance, if you're basically, even within Canada, the population is about 33 million. If you wanted to figure out, say, the average salary or so on and so forth, it's going to be pretty difficult to survey every single person. Then what we do is we basically randomly select a subset. So this is going to be a sample, is a subset that we select. So we want to make sure that the sample actually has the same characteristics as the representation over here. There are different ways in which you can basically draw your sample. So the first one is a simple random sample. Each sample is very likely. The next one is a stratified sample. Here we divide the population into different groups and take some samples proportional to the different groups. So you can basically stratify, say, based on the age, number of years in college. You might basically stratify based on the income group, and then you can basically, based on the number of population, you can stratify and then pick sample accordingly. So the next one is a clustered sample, where we divide the group of the population into different groups or clusters, and then randomly select some cluster to actually do our sampling. So there are other methods where you might be a systematic sampling, where you have a starting point and then you take the nth sample, and then there might be a convenience sample, and then where basically think about whoever is willing to take a survey on your website. That might be a convenience sample or some sample that you might already have. So when you analyze your data, it is important to be aware of some sampling errors. So what do we mean by that? The sampling process itself causes some errors. The sample may not be large enough. For instance, if I wanted to survey the population of Canada, if I just select me and my buddy, that's not going to be a very large sample. There might be some contributing factors not related to sample. Example, so you have a device, you're counting, and there might be error. And if you, I don't know, you might have heard about the story. So UK was basically using an old version of Excel to store all the COVID information, and then the Excel doesn't go beyond 32,500 or so rows, and so they basically lost a bunch of data. They didn't lose it, but that's kind of the end of it. That might be some issues as well. So in statistics, anyway, coming back, in statistics, we need to be aware of sampling bias. Or a sampling bias is basically created when a sample is collected from a population and some members of the population are not likely to be chosen. So when a sampling bias happens, there can be incorrect conclusion that can be drawn about the population. So an example would be if you call up just your buddies to determine the best universities. So for instance, if you call up all of your friends in SFU, ask them the best university, they're probably going to be telling you that SFU is the best university. I'm not saying that's incorrect, but I'm just saying that there might potentially be a sampling bias in that case. So then the next thing we have to do is basically kind of be aware of potential sampling errors. So when we read, and then we have to critically evaluate all of this stuff. So basically, so we have to examine if there is some problem with the sample. So the sample might be representative, and there shouldn't be any bias. There could potentially be like self-selection with the sample. So responses only from people who choose to respond to it, such as a call-in survey, are often unreliable. The other case might be where, for instance, if you look at Amazon, now there's a controversy where seller is giving out cash incentive and then to select like better experience and then rating. So that could cause some sampling issues. There might be issues with the sampling size. So if the sample size is too small, obviously a larger sample is better. So too small a sample might be unreliable. In some crash testing or medical device training, so there might be some rare conditions which might be missed, or the way in which the question is actually framed could influence the data that's basically being collected. There could also be some undue influences and which would basically question, which actually reminds me of a very good video. So I'll post a link. So this is a video regarding leading questions from the show called Yes Prime Minister, and then where, again, I don't condone the language in there, but then you can take a look at this video. It's actually kind of interesting as to what could be a potential cause of issues with sampling. So then the other issues with sampling would be non-response or refusal for the subject. So the collected sample may no longer be representative of the population. Often people with strong positive or negative opinions might actually give a response, and you may not actually get a very good representation. And then there is an issue with causality. So what that means is you might actually observe some things that are occurring together, and then you might actually think about or conclude that one is causing the other, but they not always be true. So the next one is self-funded or self-interest studies. So a study performed by a person or an organization in order to support their claims. So then we have to evaluate, could it really be impartial? And then then you have to look at and then evaluate the merits of the study. And so there could be a potential source of bias there. There could also be like misleading use of data, so improper graph, so you might x-axis, or it could be incomplete data, so they might have dropped some data, so or a lack of context, so all of those could lead to misleading conclusions. And then there could be a concept of confounding variables, where basically multiple factors could be affected and then they cannot be easily separated, and then this could make essentially drawing of valid conclusion very difficult. So to kind of give you an idea, so essentially, so last year, simple example, Seaside Surf City, California. So the mayor basically promised to do something about the increased shark attacks. So they basically said if you plot the ice cream sales versus the shark attack, they basically noticed that they're related to each other. So then would it be valid for the mayor to basically say, I'm going to ban all ice creams in the summer in order to reduce shark attacks? So this might be a simple question. So where this actually looks at two different things. Firstly, the relation between causality and correlation, and also the potential source of a confounding variable. So if we take actually a step back and look at it, you can see that when there is a heat wave, the ice cream sales are likely to go up, and then the number of people going to the surf might also increase. Then the heat wave might actually be causing both of them, and then so you shouldn't actually make an incomplete or incorrect conclusion that ice cream sales basically increases shark attack. Anyway, so quickly to summarize the section over here, so if you completed the section, so you should be able to explain the different types of data. We basically explained the concept of sampling, and then we looked at the different sources or potential sources of error here. So next, we're going to be looking at data organization. So just a quick word of caution or just a good practice is when you're basically doing any data manipulation or manipulating the answer, so then, or maybe like adding numbers and so on. So generally you want to round off with respect to rounding off, you want to try to carry a few more decimal places, at the very least one more decimal place, and then round off only at the very end when you're basically doing a calculation. So there are coming back with respect to data classification. So you can basically do it in four levels of measurements. So they are on a nominal scale. So that means the data is typically qualitative. So these could be categories, colors, names, labels, favorite food, etc. So nominal scale data is usually not ordered. For instance, we typically don't order or classify people based on the favorite food. Doesn't really make sense. I mean, to you it might, but it doesn't make any sense to order say strawberries ahead of vanilla or whatever. Maybe do it randomly or alphabetically. We don't really have a specific order to it. Again, so you can again putting pizza ahead of sushi doesn't make sense in a similar way. The next scale is the ordinal scale. So here, the ordinal scale, the data is ordered, even though we cannot use it for calculation, but we use it for any measured differences. So an example would be the list of the top 5 national parks in the United States. So the next scale that we use is the interval scale. So then values can be measured, but the starting point itself doesn't have any like physical meaning to it. So temperature scales like Celsius and Fahrenheit are an interval scale. So the 0 in both of these are essentially arbitrary. So 80 Celsius is not 4 times hotter than 20 Celsius, but then ratios actually make sense. On a note, the Kelvin scale is actually an absolute scale because the absolute 0 is actually a physical 0, and then basically a temperature of 200, and is half as hot as a temperature of 400, then you're dealing with efficiencies of thermodynamic efficiency. So the Kelvin scale is a little bit different. So the next scale that we use is the ratio scale. So scale has a definite 0. Then we can take ratios here. For instance, a final exam score or the speed, they all have a specific 0, and then we can take a scale based on that. So next we're going to be looking at frequency table. So first we'll define what a frequency is. So frequency is the number of times a value occurs in a data. A value of data actually occurs. So we can think about relative frequency, or is a fraction or the proportion of the number of times the value occurs in a data relative to the sample or the population size. Cumulative so this will be obtained by dividing each frequency by the total number of samples. Cumulative frequency is the sum of all the previous frequencies. This is when you're actually ordering data, so then you can basically think about the number of samples of people less than say 5 feet, and then you can add the people who are less than 4 feet, less than 3 feet, and so on. So then you can do a cumulative frequency. So this is basically done by adding all the previous values to the current data. So we can look at a very simple example here. So essentially 20 students were asked how many hours they work per day, and then these are the responses that are listed below, and then we can calculate all of these. So you have the number 5, 6, 3, 3, so on. You can read that, and then you can pause this video and then complete this table now. So we fill in, so we count, so we have 2, data value of 3, and then we have 5, 3, 6, 2, and 1. So this is basically coming from the count here, and then we can add all of this, that comes to 20. Then we can do a relative frequency. What we do in that case is we take this value and divide it by the total. Then we can do 3 by 20 is 0.15, and keep doing that for all of the other values. And then now if I add all of these relative frequencies, I should get 1, because the denominators here are the same, and the numerator, if you did the math properly, should add to this value over here. You can do a cumulative frequency or a cumulative relative frequency. What that means is you can either add all of these values or all of these values. In this case, we are looking at a cumulative relative frequency. In that case, the first row is going to be 0.15. Second row is going to be 0.15 plus 0.25. That gives me 0.40. And then for the third one, we have to add all of these values. Or what I can do, since I've already added these two values here, I can add 0.4 and 0.15. That gives me 0.55. Then we keep going, we get 0.85, 0.95, and the last row should hopefully be 1 if you do the calculation again correctly. So we're coming very close to the end. So what we're going to be discussing very briefly is the experimental design and ethics. We do have a more elaborate discussion on the experimental design from the perspective of randomness and so on, but this is more like a general introduction. So typically what we have is we would, with our experiments, want to find the relation between 2 or more variables. So we typically have a variable known as the explanatory variable, which is the cause, and then we have a response variable, which is effect. So then what we do is we can manipulate the experimental variables and measure the change in the response. So an example would be if change the number of hours you study, that would be an explanatory variable or a cause that you can actually change. And then if you look at the effect of your score in the final exam, so that will be an effect or a response that we actually come about. So you can actually look at the similar experiment. Similarly, you can maybe change the number of hours you sleep, and then you can look at how awake you are in the rest of the day, or maybe measure it in number of cups of coffee you would need in the next day. Or you can basically look at multiple explanatory variables and then look at one or more response variables. So a different value for the explanatory variables are called as treatments, and then the experiment unit is a single object or an individual to be measured. So any study involving human test subjects needs an ethics approval. So this is very important. So university or research institutions typically have an institutional review board, and then all planned studies should go through them. And so this basically is used to minimize the risk to the participants and then to obtain what's known as informed consent. Means that patients or the group are actually told um, shortcomings and potential side effects as well as the benefits, and then they are informed about all the consequences, and then we get them to consent if they accept or not. And then the data that is collected from individuals should be very carefully guarded for privacy because all of that is very confidential. So all of this is being would be done typically institution review board, and then you work if you're working in one of our labs at SFU or human test subject, your lab director or research supervisor. And then when you eventually do rise to that position, you would actually be briefed on the procedure that needs to be adopted in that. So the other thing is we need to employ what's known as double-blinded randomized control experiments in a study or trial. So this is basically to counter the effect of suggestions. So then the research are set aside as one, the treatment group, and then the other one is a control group. So the control group is typically given what's known as a placebo. So the placebo actually looks and feels the same as control variable. For instance, if you are doing a medical experimental study, so some people might be getting actual medication, and some people might be getting a sugar pill, which looks very similar to the actual medication but doesn't actually have any effect. And then we need to balance the effect of the active treatment. The next concept we talk about is known as blinding. So blinding is a randomization process. So this kind of avoids maybe the experimental person going and telling somebody that at a gross level, telling somebody that they're getting the placebo or they're getting actual medication, but more that there might be some suggestions where maybe the experimenter cares more about a person actually receiving the medication, so they treat them better. So that might actually affect the result. So if you're actually blinding the result, so nobody knows what's happening, and then when we go one step further, where it's known as a double-blinded test, then the people within the sample or a group, they don't know who is getting the sugar pill versus the actual sugar pill placebo versus the actual medication, and the experimenter or whoever is collecting the data, so they don't know either. So this is actually known as the gold standard, which is the double-blinded randomized controlled experiment. So double-blinded basically means nobody knows who's getting the medication or the treatment versus a placebo which doesn't have any effect. Randomized is everything is mixed, and then if you're actually doing a placebo, you actually call this as a placebo controlled as well. And then we basically would ensure that all of the results that come out are going to be fairly reproducible and they are very good quantity. And so this basically concludes our video. So if you completed this segment, so this segment would have discussed data organization, and then we talked about frequency. You should be able to explain the different types of frequency and statistics. And then we talked about experimental design and ethics. And then you should also be able to explain in this case what a double-blinded randomized control experiment would be. So if you watch this video, thank you for your time. And then we'll continue for the next week where we'll discuss more definitions and actual calculations with respect to probability. So next, we're going to be looking at data organization. So just a quick word of caution or just a good practice is when you're basically doing any data manipulation or manipulating the answer, so then, or maybe like adding numbers and so on. So generally you want to round off with respect to rounding off, you want to try to carry few more decimal places, at the very least one more decimal place, and then round off only at the very end when you're basically doing a calculation. So there are coming back with respect to data classification. So you can basically do it in four levels of measurements. So they are on a nominal scale. So that means the data is typically qualitative. So these could be categories, colors, names, labels, favorite food, etc. So nominal scale data is usually not ordered. For instance, we typically don't order or classify people based on the favorite food. Doesn't really make sense. I mean, to you it might, but it doesn't make any sense to order say strawberries ahead of vanilla or whatever. Maybe do it randomly or alphabetically. We don't really have a specific order to it. Again, so you can again putting pizza ahead of sushi doesn't make sense in a similar way. The next scale is the ordinal scale. So here, the ordinal scale, the data is ordered, even though we cannot use it for calculation, but we or use it for any measured differences. So an example would be the list of the top 5 national parks in the United States. So the next scale that we use is the interval scale. So then values can be measured, but the starting point itself doesn't have any like physical meaning to it. So temperature scales like Celsius and Fahrenheit are an interval scale. So the zero in both of these are essentially arbitrary. So 80 Celsius is not 4 times hotter than 20 Celsius, but then ratios actually make sense. On a note, the Kelvin scale is actually an absolute scale because the absolute zero is actually a physical zero, and then basically a temperature of 200 and is half as hot as a temperature of 400 when you're dealing with efficiencies of thermodynamic efficiency. So the Kelvin scale is a little bit different. So the next scale that we use is the ratio scale. So scale has a definite zero. Then we can take ratios here. For instance, a final exam score or the speed, they all have a specific zero, and then we can take a scale based on that. So next we're going to be looking at frequency table. So first we'll define what a frequency is. So frequency is the number of times a value occurs in a data. A value of data actually occurs. So we can think about relative frequency, or the fraction or the proportion of the number of times the value occurs in a data relative to the sample or the population size. Cumulative so this will be obtained by dividing each frequency by the total number of samples. Cumulative frequency is the sum of all the previous frequencies. This would when you're actually ordered your data, so then you can basically think about the number of samples of people less than say 5 feet, and then you can add the people who are less than 4 feet, less than 3 feet, and so on. So then you can do a cumulative frequency. So this is basically done by adding all the previous values to the current data. So we can look at a very simple example here. So essentially 20 students were asked how many hours they work per day, and then these are the responses that are listed below, and then we can calculate all of these. So you have the number 5, 6, 3, 3, so on. You can read that, and then you can pause this video and then complete this table now. So we fill in, so we count. So we have 2, data value of 3, and then we have 5, 3, 6, 2, and 1. So this is basically coming from the count here, and then we can add all of this. That comes to 20. Then we can do a relative frequency. What we do in that case is we take this value and divide it by the total. Then we can do 3 by 20 is 0.15, and keep doing that for all of the other values. And then now if I add all of these relative frequencies, I should get 1 because the denominators here are the same, and the numerator, if you did the math properly, should add to this value over here. You can do a cumulative frequency or a cumulative relative frequency. What that means is you can either add all of these values or all of these values. In this case, we are looking at a cumulative relative frequency. In that case, the first row is going to be 0.15. Second row is going to be 0.15 plus 0.25. That gives me 0.40. And then for the third one, we have to add all of these values. Or what I can do, since I've already added these two values here, I can add 0.4 and 0.15. That gives me 0.55. Then we keep going, we get 0.85, 0.95, and the last row should hopefully be 1 if you did the calculation again correctly. So we're coming very close to the end. So what we're going to be discussing very briefly is the experimental design and ethics. We do have a more elaborate discussion on the experimental design from the perspective of randomness and so on, but this is more like a general introduction. So typically what we have is we would, with our experiments, want to find the relation between 2 or more variables. So we typically have a variable known as the explanatory variable, which is the cause, and then we have a response variable, which is effect. So then what we do is we can manipulate the experimental variables and measure the change in the response. So an example would be if change the number of hours you study. That will be an explanatory variable or a cost that you can actually change. And then if you look at the effect of your score in the final exam, so that will be an effect or a response that we actually come about. So you can actually look at the similar experiment. Similarly, you can maybe change the number of hours you sleep, and then you can look at how awake you are in the rest of the day, or maybe measure it in number of cups of coffee you would need in the next day. Or you can basically look at multiple explanatory variables and then look at one or more response variables. So a different value for the explanatory variables are called as treatments, and then the experiment unit is a single object or an individual to be measured. So any study involving human test subjects needs an ethics approval. So this is very important. So university or research institutions typically have an institutional review board, and then all planned studies should go through them. And so this basically is used to minimize the risk to the participants and then to obtain what's known as informed consent. Means that patients or the group are actually told shortcomings and potential side effects as well as the benefits, and then they are informed about all the consequences, and then we get them to consent if they accept or not. And then the data that is collected from individuals should be very carefully guarded for privacy because all of that is very confidential. So all of this would be done typically institution review board, and then if you're working in one of our labs at SFU, which is called human test subject, your lab director or research supervisor. And then when you eventually do rise to that position, you would actually be briefed on the procedure that needs to be adopted in that. So the other thing is we need to employ what's known as double-blinded randomized control experiments in a study or trial. So this is basically to counter the effect of suggestions. So then the research are set aside as one, the treatment group, and then the other one is a control group. So the control group is typically given what's known as a placebo. So the placebo actually looks and feels the same as control variable. For instance, if you are doing a medical experimental study, so some people might be getting actual medication, and some people might be getting a sugar pill, which looks very similar to the actual medication but doesn't actually have any effect. And then we need to balance the effect of the active treatment. The next concept we talk about is known as blinding. So blinding is a randomization process. So this kind of avoids maybe the experimental person going and telling somebody that at a gross level, telling somebody that they're getting the placebo or they're getting actual medication, but more that there might be some suggestions where maybe the experimenter cares more about a person actually receiving the medication, so they treat them better. So that might actually affect the result. So if you're actually blinding the result, so nobody knows what's happening, and then when we go one step further, where it's known as a double-blinded test, then the people within the sample or a group, they don't know who is getting the sugar pill versus the actual sugar pill placebo versus the actual medication, and the experimenter or whoever is collecting the data, so they don't know either. So this is actually known as the gold standard, which is the double-blinded randomized controlled experiment. So double-blinded basically means nobody knows who's getting the medication or the treatment versus a placebo, which doesn't have any effect. Randomized is everything is mixed. And then if you're actually doing a placebo, you actually call this as a placebo controlled as well. And then we basically would ensure that all of the results that come out are going to be fairly reproducible and they are very good quantity. And so this basically concludes our video. So if you completed the segment, so this segment would have discussed data organization, and then we talked about frequency. You should be able to explain the different types of frequency and statistics. And then we talked about experimental design and ethics. And then you should also be able to explain in this case what a double-blinded randomized control experiment would be. So if you watch this video, thank you for your time. And then we'll continue for the next week where we'll discuss more definitions and actual calculations with respect to probability.